Welcome back, Focus Learners, to another explainer. Today, we are cracking open a seriously fascinating piece of engineering from GitHub. Specifically, we're looking at a highly technical, incredibly well-structured repository by a developer named Saikaran Ramayanam. It's a project entirely dedicated to catching those invisible errors that hide deep within endless streams of data.
Okay, let's dive into this. Here is our roadmap for today. We'll start with the blueprint, move on to the engine, check out the detection mechanism, look at refining the signal, and finally wrap up with the user experience.
Section 1. The Blueprint. Goal of the project.
So the core mission of this entire project is unsupervised anomaly detection. What does that actually mean? Well, it's a system designed to find hidden, abnormal patterns in time series data without needing any pre-labeled examples. And you might be wondering, why is this so absolutely crucial? Because in the real world, whether we're talking about monitoring server health, wild stock market fluctuations, or just sensors on a manufacturing line, you almost never have a perfectly labeled data set telling you exactly what an error looks like in advance. You really need a system that's smart enough to figure out what normal behavior looks like entirely on its own so it can automatically throw a flag when something goes off the rails.
Section 2. The engine. Mathematical foundation.
All right, let's look under the hood at the sheer power of the components assembled here. The primary workhorse driving this whole repository is a temporal convolutional network, or TCN autoencoder, and it's backed by some highly specialized techniques, namely causal convolutions and dilated convolutions. Oh, and as a quick fun detail for the developers watching, this absolute powerhouse of an engine is built almost entirely in Python. We're talking 98.9% of the codebase. It's just a remarkably clean, focused, and highly specialized software stack.
The architecture here brilliantly illustrates how these complex convolutions work in tandem to process time series data without cheating. On one side, we have causal convolutions. This ensures strict chronological discipline. It literally guarantees that the model processes data sequentially and is only allowed to look at the past, so absolutely no data leakage from the future. On the flip side, we have dilated convolutions. This expands the model's receptive field, which essentially allows the neural network to skip steps and recognize much broader long-term patterns over time, all without needing some infinitely deep memory-hogging network. Put them together and you've got an incredibly efficient context-aware engine.
Section 3. The detection mechanism. Catching bad data.
So, how does this thing actually catch anomalies? It all comes down to a three-step data journey. Step 1. Your raw time series data enters the TCN autoencoder. Step 2. The autoencoder compresses that data into a tiny representation and then attempts a full reconstruction of the original data. It's basically trying to draw the data sequence from memory based purely on what it learned was normal. And finally, Step 3. We measure the difference between the original data and the model's reconstruction. If the system struggles to rebuild a specific data point, it spits out a high reconstruction error. Think of it like a highly advanced game of spot the difference. A massive error means the incoming data was so weird, so out of left field, that the model just couldn't recreate it. Boom, that flags your anomaly.
Section 4. Refining the signal. Setting the threshold.
Now, this brings up a huge question. How do we set the exact threshold for an anomaly? I mean, if the system flags every single tiny discrepancy, you're going to be completely drowning in false alarms, right? The tool becomes useless. But if you set the threshold too high, you might completely miss a catastrophic failure. We need precise mathematical tools to draw that boundary line dynamically.
And that's exactly what this repository solves, using three specific statistical features. First up is EMA smoothing, or exponential moving average. This essentially applies a filter to smooth out all those noisy, everyday fluctuations in the data so we can actually see the true underlying trend. Second, we've got percentile thresholding. So instead of using a rigid, static number, this flags errors dynamically based on percentile rankings, adapting on the fly to the data's unique distribution. And third is POT thresholding, which stands for peaks over threshold. This is a super advanced technique specifically designed to isolate and flag extreme outlier values based on extreme value theory. By combining these three methods, the model drastically refines the signal. No more false alarms.
Section 5. The user experience. Interactive deployment.
You know, the creator didn't just leave this as a bunch of abstract back-end scripts for us to figure out. The project actually includes an interactive Streamlit dashboard for visualization. I really want to emphasize the word interactive here.
Streamlit is brilliant for this because it takes all of that heavy TCN autoencoder complexity we just unpacked and packages the whole shebang into a clean visual web interface. This means a data scientist or an operations engineer can actually view the time series data and see the anomalies being flagged clearly right there on a graph.
And to top it all off, we have seamless deployment with Docker support. This really shows the creator's foresight regarding actual real-world deployment. The repository includes a Docker file and a Docker Compose setup. You know what that means? You don't have to spend days pulling your hair out fighting with Python dependencies or environment variables just to get this running locally. The entire environment is containerized, meaning this project is literally deployment ready right out of the box.
So what does this all mean for us? Let's leave off with a bit of a provocative thought. As the time series data we rely on grows infinitely more complex across every single industry, could this unsupervised TCN approach actually become your new standard for catching those invisible errors? This repository offers a remarkably robust, highly deployable blueprint for doing exactly that. I highly encourage you to head over to GitHub, explore the codebase for yourself, and see how you might apply it to your own data streams. Thank you so much for joining me for this explainer, and as always, keep learning.